Hello everyone. So in this pre-lecture tutorial, we're going to start to correlate what we've learned regarding the structure of molecules and polyatomic ions to their function and to their behavior in chemical systems. And so in order to understand that, we have to begin by looking at an atomic property related to atoms that are bonded together that's called electronegativity. Now, electronegativity is the tendency of an atom to attract electrons towards itself within a chemical bond. So suppose that I have two atoms bonded together. Suppose one of them is a hydrogen and the other one's a fluorine. Okay? Now, since these two atoms are different from one another, it's entirely possible that the two electrons within the chemical bond might actually not be shared equally here. That wouldn't be the case, say, if I had two hydrogens bonded to each other. In the case of this particular molecule, since the atoms are the same on either side of the chemical bond, then the electrons are shared exactly equally. But when the atoms are different, that may not be the case. It may be possible that one of these atoms might pull on those two electrons a little bit more strongly than the other atom. And so the way to figure that out, if that's the case, is to take a look at this property of electronegativity. Now, the way that electronegativity works is the smaller the atom and the more positive the nucleus for that small atom, then the stronger the attraction for the electrons. And so when we consider the periodic table as a whole, the smallest atom with the most positive nucleus that's capable of forming bonds under normal circumstances would be fluorine. And so as a result, fluorine has the highest electronegativity out of all of the atoms in the periodic table. And if you take a look at the periodic table in greater detail, basically you have fluorine in every direction. As you move away from fluorine, the electronegativity drops. So if I go down a group in the periodic table, then the electronegativity decreases. If I move away from fluorine going to the left within a period, then also the electronegativity decreases. Now, in terms of elements with very low electronegativity, then that would be metals. Metals tend to be larger atoms. Their nuclei tend to be not as positive compared to other elements within the same period. And so as a result, diagonally across from fluorine in the periodic table would be cesium. And if you notice, cesium actually has the lowest electronegativity out of all of the elements in the periodic table that we know at this point. Now, in general, all right, if I want to figure out what type of bond I might have, whether I have one of these bonds where the electrons are shared equally or if the electrons are shared unequally, then if I take the difference in electronegativity, then that would actually help me to decide whether the electrons are shared equally or not. Now, typically when we consider these electronegativity values and their differences, we can actually break down bonds into three main types. There are nonpolar covalent bonds, which is where the electrons are shared essentially equally. We have polar covalent bonds where the electrons are shared unequally. And then we have ionic bonds in which an electron is fully transferred from one atom to the other. Now notice I can correlate the electronegativity difference to each type of bond. So if my electronegativity difference, which is essentially just the absolute value of the difference between the two electronegativity values, is between 0 to 0.4, then my bond is nonpolar covalent. If I have an electronegativity difference of 0.5 to 1.8, then my bond is polar covalent. And that would mean that the electrons are shared unequally. Notice that when that happens, basically the atom that has the lower electronegativity develops what we call a partial positive charge. And that atom that has the higher electronegativity has what we call a partial negative charge. It's not a full positive or a full negative charge, as is the case for ionic bonds. But basically all this implies, this concept of partial charges, is that one side of the bond is a bit more negatively charged than the other side because of the difference in electronegativity. And if I have a difference in electronegativity of 1.9 to 3.3, then that would correspond to an ionic bond. So let me give you guys an example of applying that rule, and then we'll do some additional examples, and then you guys can try the follow-up assignment. Suppose I have a bond in which hydrogen is bonded to bromine. And so what I would want to do is calculate the difference. So basically this triangle is the Greek letter delta, so that means difference in the electronegativity values. Okay, so the first thing I need to do is find the electronegativity for each of these. So if I take a look at my chart, the electronegativity for hydrogen is 2.1, but for bromine, the electronegativity is 2.8. So 2.1 for hydrogen, 2.8 for bromine. And like I said, we want to take the absolute value of this difference. So it's 2.8 minus 2.1, that would be an electronegativity difference of 0.7. If I look this up in the chart above, that would fall within this range. So that would mean that the bond between hydrogen and bromine is considered to be polar covalent. And since hydrogen has the lower electronegativity, then it has a partial positive charge, whereas the bromine, since it has the higher electronegativity value, it would have a partial negative charge. Okay, let's do a few more of those examples. So how about hydrogen and chlorine? So I'll look up in my electronegativity table, like we said, hydrogen is 2.1, but chlorine is 3.0. So 2.1 for hydrogen, 3.0 for chlorine. The difference in electronegativity for this particular bond would be 0.9. If I consult my chart, then 0.9 falls in the range of a polar covalent bond. Since hydrogen has the lower electronegativity, it would have a partial positive charge, and since chlorine has the higher electronegativity, it would have a partial negative charge. If I take a look at two hydrogens bonded together, each of them would have an electronegativity of 2.1. So if I take the difference in the electronegativity, then that would be an electronegativity difference of 0.0, which correlates to a nonpolar covalent bond. Okay, and if I don't have a polar covalent bond, then there are no partial negative or partial positive charges to assign. Let's take a look at hydrogen and iodine. Hydrogen's electronegativity is 2.1, as we've seen above. The electronegativity for bromine is 2.8. I'm sorry, the electronegativity for iodine is what we're looking for here. The electronegativity for iodine is 2.5. Okay, so that means that the change in electronegativity, or the difference in electronegativity between these two atoms, is 0.4. Okay, and 0.4 would actually be right on the limit of what we consider to be nonpolar covalent. So here's an example where the electronegativity difference is too small that we wouldn't necessarily consider this to be a polar covalent bond. If I have two bromines together, then basically bromine, if I look up bromine's electronegativity, that's 2.8, right? But then that would be each bromine with an electronegativity of 2.8. So here's another case where the difference in electronegativity is 0.0. So it would also be considered a nonpolar covalent bond. And if I take a look at a carbon-oxygen bond, notice that the presence of the double bond doesn't really change anything. I'm still going to apply the same system. Carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. And so that means that for this bond, the change in electronegativity, or the difference in electronegativity, would be 1.0. And again, checking our table, that falls right in the range of a polar covalent bond. And so that would mean that since carbon has the smaller electronegativity, then that would actually have a partial positive charge. Since oxygen has a greater electronegativity, it would have a partial negative charge. Okay, so go ahead and try the exercises within the follow-up assignment. All right, go ahead and read the corresponding section of the book as well. If you have any questions, by all means email, or if not, bring up your questions in class tomorrow. All right, have a good night.